Hello everyone, I'm Haesung Jin in Defendable Lab in Computer Science Department. My paper is about asking clarifying questions in open domain information seeking conversation. It is about the task of asking clarifying questions in conversational system just like title. This paper was written by Aliani Jardi et al. In SIGIR 2019. Here is my content. First of all, I let you know about a possible problem while you are searching information in open domain. And then I'll figure out some challenges in the problem. For the next step, you'll get some meaning of proposed approach and details. Finally, I'll show you some analysis about performance of proposed approaches. Users often fail to formulate their complex information need in a single query. There's lots of web pages related that query artificial intelligence. As a consequence, they may need to scan multiple result pages or reformulate their queries, which may be a frustrating experience. Here is a very simple example. I would input automobile to find car imagery or magazine named by automobile. However, search engine cannot know about user's intention with only one query. Clarifying question is needed. The problem of asking clarifying question is particularly interesting in case where a query can be interpreted in various ways. The user information need is not clear from the query. Asking clarifying questions is especially important in conversational search system for two reasons. First reason, conversation is the most convenient way for natural language interactions and asking questions. Second reason, a conversational system can only return a limited number of results. Thus, being confident about the retrieval performance becomes even more important. A key advantage of conversational search system is to ability to interact with the user in form of question and answer. Conversational search system can proactively pose question to understand user actual information need more accurately. It improves its confidence in a search result. As I said previous slide, to solve the problem of ambiguous query, system can ask questions to user to clarify user's intent before return the result. This example shows conversation selected from dataset. There is to user Alice and Robin issue the same query dinosaur. However, their actual information needs are completely different. With no prior knowledge, the system starts with the same clarifying question. Depending on the user's answer, the system selects the next question in order to clarify the user's information need. The tag no answer shows that the asked question is not related to the information need. In fact, the user response aids the system to get a better understanding of the underlying information need. This is workflow for asking clarifying questions. Alice initiates the conversation by submitting her query to the system. The system retrieves list of documents and estimates confidence on the result list. If the system isn't sufficiently confident to present the result to the user, then start the process of asking clarifying questions. As a first step, it generates a list of confident questions related to Alice's query. Next, The system selects the question from the candidate question list and asks it from the user. Based on Alice's answer, the system retrieves new document and repeats the process. The solution of this problem relates information retrieval and NLP. Also, result diversification and personalization is one of the key components for query suggestion. Much work has done on interacting with users for recommendation. For example, Sun and Zhang utilize a semi-struct user query with packseed value field to represent the conversation history. Propose a deep reinforcement learning framework to build a personalized conversation recommender system. Here is challenges for this work. To implement the conversational search with clarifying question, it needs three components. There is question retrieval, question selection, and document retrieval using offline evaluation protocol. The design offline evaluation protocol is challenging because conversation requires online interaction between user and system. Hence, offline evaluation strategy require human-generated answer. To solve this, they substitute the question generation model in figure with a large bank of questions, assuming it consists of all possible questions in the collection. Here is problem statement. Let T be a set of topics and initiate the conversation, and F as a set of packets with Fi define different packets of Ti. Let Q the set of clarifying questions belonging to every topic consists of all clarifying questions. The aim is to provide the user's answer to the clarifying question, considering all topics and their corresponding packets. Therefore, let function A TFQ is A. Define a function that returns answer A, a given topic T, packet F, and question Q. T and F are borrowed from the web track from 2009 to 2012 data. Q is then collected via crowdsourcing, and function A is also modeled by crowd function. To the experiment, dataset is built on top of TREC web track data as before I said. It consists of over 10,000 question and answer pairs for 198 TREC topics with 762 facts. In the first step, they define the topics and their corresponding facts. In the second step, they collect a number of candidate clarifying questions for each query through crowdsourcing. Then, in the first step, they assess the relevance of the question to its passage and collect new questions for those passages that require more specific questions. Finally, the last step, they collect the answer for every query, facet, question, triple modeling A. They take the topic of TREC data as initial user query, then break each topic into the passage. They assume that each passage describes the information need of a different user. To collect clarifying questions, they design a Human Intelligence Task HIT on Amazon Mechanical Turk. They assign 2 workers to each HIT, resulting in 12 questions per topic in the first round. The process is like this. First, enter the same query in a search engine of their choice and scan the result in the first 3 pages. Second, Using autocomplete suggestion, the worker finds the query reflects various aspects of the same query. Third, the worker generates 6 questions related to the query, aimed to address the facts that they have figured out. After collecting the clarifying questions, the next step is verifying them for quality assurance. In question verification and addition step, there is 2 main concerns. First, how good are the collected clarifying questions? Second, are all facts addressed by at least one clarifying question? After collecting and verifying the question, they design another HIT in which they collect answers to the question for every facet. They propose a conversational search system that is able to select and ask clarifying questions and rank documents based on the user's response. This system consists with question retrieval model, question selection model, document retrieval model. They propose system retrieve a set of questions for a given query from a large pool of questions containing all the questions in the collection. At the second stage, proposed model, called new QS, aim to select the best question to pose to the user based on the query and the conversation context. This problem is particularly challenging because the conversational interactions are the natural language, highly depending on the previous interaction between user and the system. They present BERT language representation-based question retrieval model called BERT-ReQR. Retrieving all relevant questions from a large pool of questions is challenging because questions are short and context-dependent. BERT-ReQR estimates the probability where R is a binary random variable indicating whether the question Q should be retrieved R equal 1 or not R equal 0. T and Q denote the query and the candidate clarifying question. They implement pi_t and pi_q similarly using a function that maps a sequence of words to a d-dimensional representation. They use a BERT model to run these representation functions. BERT is a deep neural network with 12 layers that use an attention-based network called transformers. They present a neural question selection model which selects questions with a focus on maximizing the precision at the top of the ranked list. UQS incorporates multiple sources of information. It learns from similarity of the query, a question, and the context, as well as retrieval and performance prediction signals. UQS outputs a relevance score for a given query T, question Q, and conversation context H. Further, the context representation component pi_h is implemented as pi_qa is an embedding function of a question Q and answer A. Finally, query performance prediction QPP representation component sigma THQ of the performance prediction score of the ranked document at different ranking position. They use KL divergence retrieval model based on language modeling framework with declared prior smoothing, where they linearly interpolate to likelihood model, one based on original query and the other based on the question and their respective answer. For every term W of original query T, conversation context H, the current question Q and answer A, the interpolate query probability is computed as equation 1, where zeta T denotes the language model of an original query and zeta HQA denotes the language model of a question and answer that have been exchanged in the conversation. Alpha denotes the weight of the original query and it turns on the development set. And the score of document D is calculated as equation 2, where T is the set of all terms present in the conversation. Now I explain about experiment and result. They evaluate both LQR and UQS on QLOG, 5-fold cross-validation. They follow two strategies to split the data. They split the trained validation test set based on topic, and they split the data based on their fixed. They consider 4 metrics to evaluate the effectiveness of question retrieval models: means, average precision, MAP, and recall for the top 10, 20, and 30 retrieved questions. The measure is achieving high recall for the task. The paper solution is able to outperform all baseline. The measure of question selection is mean reciprocal length MRR, precision of the top 1 retrieved document P at 1, and normalized discounted cumulative gain for the top 1, 5, and 20 retrieved documents. They choose MRR to evaluate the effect of asking clarifying questions on ranking the first 11 documents. They report P at 1 to measure the performance for scenarios where the system is able to return only one result. For sigma QPP, they use a simple effective query performance predictor. For lambda math RankNet, they consider the task of question selection as a rank problem, where a list of candidate questions should be ranked and the one with the highest rank is chosen. For this, they use LTR baseline. As a result, new QS constantly outperform all the baseline in terms of all evaluation metric on both data split. Now we see impact of data split. They compare the performance of model on both QLOG-T and QLOG-F data split. UQS exhibit a significant improvement in terms of all evaluation metric on QLOG-F. They also evaluate the impact of number of conversation turns. We see that UQS exhibit robust performance, outperforming all the baseline at different turns. They analyze representative case of failure and success of proposed framework. They list 3 cases where selecting questions using UQS improved the retrieval performance, and there are 3 another examples in which the selected question lead to decreased performance. Now I will explain 4 examples. In first row in table, we see that even though the user has provided additional information, the performance drops. This is maybe due to existence of no common term between the additional information. The third row of the table shows another failure example where the selected question is not relevant to the facts and the user provides no additional information. The first successful example in fourth row is where the system is able to ask an open question is more likely to get useful feedback from user in response to such questions. The last example shows a case where the answer is negative, but the user is engaged in conversation and provide additional information about the facts. There are some limitations of this study. First, the dataset was not collected from actual conversation. Second, QLA is built for single-tone conversation. The data collection approach does not guarantee the existence of multi-tone conversation that involve the same participant. Also, the quality of generated clarifying questions highly depend on how well the selected commercial search engine is able to diversify the result list. They aim to minimize this bias by asking workers to scan at least 3 pages of the result list. Also, the question added by expert annotator guaranteed the coverage of all facts. Paper's main focus was on question selection. There are various directions that can be explored in the future. One interesting problem is to explore various strategies of improving the performance of document retrieval model as new information is added to the model. This is all my presentation. Thank you for the listening.